In this lesson, we're going to talk about experimental probability and also theoretical probability. Then we're going to discuss sample space and events. So first of all, experimental probability, also known as relative frequency. So if you perform an experiment many times and you record the outcomes and the frequency of those outcomes, so how often those outcomes occur, then the experimental probability of an outcome is the frequency of that outcome divided by the total number of trials. So if you're tossing a coin and you do it, let's say 100 times, and you're recording how many times you got heads and how many times you got tails, and if you ended up with 52 heads, that would be the frequency of heads. And so based on your experiment, the probability of getting heads is 52 out of 100. 52 being the frequency of heads, 100 being the number of trials. So, people exiting a new ride at a theme park were asked whether they liked or disliked the ride, and the results are in this table. This is called a two-way table because it has two types of criteria. One is whether the person was a child or an adult, and the other is whether the person liked or disliked the ride, or at least claimed to like or dislike the ride. So those are the two different categories that you've split. Now, a two-way table could have multiple of these or multiple of these, but it would only have one set of rows and one set of columns. Now, whenever you have a two-way table, before you do anything else, you first calculate subtotals and the grand total. So, for example, the subtotal of children is 72, and the subtotal of adults is 58, and of course I just added these two to get that one, added these two to get that one. And then the subtotal of people who liked the ride is 83, and then the subtotal of people who did not like the ride is 47, and then the grand total is these two added up together, or for that matter, these two added up together. They better be the same thing. So the grand total here is 130. Now that 130 is the total number of trials because we asked 130 people whether they liked or disliked the ride, and then the various answers and whether they were children or adults were recorded, and so we can now ask questions about the various outcomes that happened. So we want to find the probability that a person selected at random liked the ride. So we write it this way, probability of liked. Well, we need to know the number of outcomes that satisfied liked. Well, that would be 83. And then we divide by the total number of trials, which was 130. And when you round this to 3 sig figs, you get approximately 0.638. Now the question is, what's the probability that the person is a child and disliked the ride? So this is the group of people that are child and disliked, or children who disliked the ride. So 17 out of the total number of trials, which is 180. So probability of child, and I'm going to write intersect for and, disliked. Well, that's in this case 17 out of 130, which is approximately 0.131. And finally, what's the probability that a person selected at random is an adult or disliked the ride? So if they're an adult, they count. If they disliked the ride, they count. And if they're both, they count. So the probability of adult or, I'm going to use union, disliked. Well, that would be these people because they're adults, these people because they're adults and they also dislike the ride, and then these people because they dislike the ride even though they're not adults. So that's 28 plus 30 plus 17 all over 130, which is 75 over 130, which rounds to 0.577. So before we do theoretical probability, I want to remind you what sample space and events are. So the sample space is the set of all possible outcomes in an experiment. We often use the letter U for universal set or S for sample space. The textbook likes to use the letter U, so I'm going to stick with that, but I have seen S, very common as well. An event is a set of outcomes that satisfy some criteria. So not necessarily the whole sample space, some subset of the sample space. Again, we use capital letters to describe an event generally if we don't use the entire word or brief abbreviation. All right, so there are multiple ways to organize your sample space, and the primary point of today's lesson is organizing your sample space. The first is the two-way table, like the problem we just did, but I actually wrote it fourth. But there's also Venn diagrams, which we've done before. There's tree diagrams with probabilities added in or included in, and there's two-dimensional grids. Eventually, we will be using all of these, but for now, we're just going to use some of them. Now, theoretical probability, we first are assuming that every outcome in the sample space is equally likely. So, for example, out of those 130 people that we asked about whether they liked or disliked the ride, when we randomly select a person, every person is equally likely to have been randomly selected. So each person was an outcome, but the different sets of like children or adults or whatever, those were events. So you got to keep outcome versus event separate. So assuming every outcome in the sample space is equally likely, then the probability of some event A is equal to the number of outcomes in event A divided by the number of outcomes in the sample space. Now, this is a theoretical probability scenario, not the experimental probability like we did with the theme park, where we asked questions and we actually performed an experiment and gathered 130 data points and then used that. Here, we're doing it purely theoretical. We say, okay, we're about to toss a coin. We won't ever toss that coin, but we're looking for probabilities based on our understanding of how coin tosses work in general. Now, all probabilities are going to be between 0 and 1. A probability of 0 is something that cannot ever happen. A probability of 1 is something that is guaranteed to happen, will definitely happen. So all probabilities are somewhere between 0 and 1. And if you find something that's not between 0 and 1, you know you did something wrong. Now, there's one other principle that's going to come in handy. We'll do it a little bit today, but it'll come in much more handy later on, which is the complement principle. If you remember, A complement or A prime is called the complement of A, is basically not A. So we're talking about everything outside of the set A, but still in the universal set or in the sample space. So because A complement and A, when you sort of look at them together, it gives you the entire sample space, we know that the probability of A plus the probability of A complement is always going to equal 1, because either A happens or it doesn't happen, and that's it. There's no other possibility, so those add up to 1. Now, this is true, but not very useful. More useful is when you subtract one of those over, so the probability of A is 1 minus the probability of A complement. So when you're doing probability questions, you will often think to yourself, is it easy to find the probability of what we want directly, or is it easier possibly to find the complement probability and then do 1 minus that probability, and that might be quicker. All right, so a ticket is randomly selected from a basket containing 3 green, 4 yellow, and 5 blue tickets. Find the probability that the ticket is A, green. So probability of green. Well, there were 3 green, 4 yellow, and 5 blue tickets, which means a total of 12 tickets. So the number of outcomes in the sample space is 12. The number of outcomes in the event G is 3, so the probability is 3 over 12. And if you want to simplify that, that's 1/4. Now, for the probability for not green, I'm going to call it green complement. Well, I could actually figure it out, well, there's 4 yellow and 5 blue, so that's 9 out of 12, and work it out that way, and that's okay. In this problem, that would not be very hard to do, but I'm going to take advantage of our complement idea. If I already know the probability of green, the probability of not green is just 1 minus the probability of green, which is, of course, going to be 1 minus 1/4, or 3/4. Now, I would be shocked if IB has a question quite this simple, but I'm trying to illustrate the idea of using the complement here. Finally, one with probability of green or yellow. Again, I'm going to use union for or. So probability of green or yellow, well, there's 3 green and 4 yellow, so 7 out of 12, and there's no simplifying that. I guess you could get a decimal. Okay, we have 2 6-sided dice which are rolled, and the sum is recorded. We want to find the probability first that the sum is 7. So what I've done here is I've created what's called a two-dimensional grid. On the horizontal axis, I called that the results of die 1, which is 1, 2, 3, 4, 5, or 6. And on the vertical axis, I called that the results of die 2, which is 1, 2, 3, 4, 5, 6. And then I put dots on all of the positions where die 1 and die 2 had results. So for example, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 2, 1, 2, 2, 2, 3, 2, 4, etc. So these are 36 different outcomes, all of which now are equally likely. Now, when you're dealing with two of something happening, like two dice or two coins or something like that, one option is to draw a two-dimensional grid in order to answer the question. Especially when you have two six-sided dice and you're looking for things like the sum. This is really the most convenient way to do it. So, if I want the sum of the two dice to be 7, probability that the sum equals 7, well, that means I have to figure out all the outcomes that have a sum of 7. So a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, a 5 and a 2, and a 6 and a 1. Those are the outcomes in this grid that add up to 7. There are 1, 2, 3, 4, 5, 6 of them out of a total of 36 outcomes. So the probability here is 6 out of 36. Or if you want to simplify that, it's 1/6. Now the question is, find the probability that the sum is not 6 or 10. So the probability that the sum is not equal to 6 or 10. Well, I could go and try to identify all the sums that are not 6 or 10, but I'm making my life too hard. I'm going to do 1 minus the probability that the sum is equal to 6 or 10. So now with a different color, I'm going to highlight all the scenarios where the sum is equal to 6, for example. So 1 and a 5, a 2 and a 4, a 3 and a 3, a 4 and a 2 and a 5 and a 1. And then for those that add up to 10, a 4 and a 6, a 5 and a 5, a 6 and a 4. So there are a total of 1, 2, 3, 4, 5, 6, 7, 8, where the sum is equal to a 6 or a 10. So 1 minus that probability would give me what I want. So in this case, 1 minus 8 out of 36. Or if you want, you can think of this as 36 out of 36 minus 8 out of 36. So it ends up being 28 out of 36. And again, you can simplify that. It's 7/9. So again, I've used the advantage, taken advantage of the complement here because it was easier to figure this probability out than it would be to figure out all the scenarios where you didn't get a 6 or a 10. All right, in a class of 30 students, 19 study physics, 17 study chemistry, and 15 study both. If one student is selected at random, find the probability that, the first question is, the student studies at least one of these. So this to me sounds like a Venn diagram problem. So I've drawn a Venn diagram. I labeled the universal set and I labeled 30 students total. And then I drew physics and chemistry. And notice I used pH for physics, not just P. P represents probability. So you're getting yourself in trouble if you use P twice, once for physics and once for probability. So I always avoid it if I remember. And then I used C for chemistry because that one was easy. And so I labeled 19 on the physics circle and 17 on the chemistry circle. And then we said that 15 studied both. So 15 was the underlying number over here. And so now I can fill in these other pieces because I know that the 15 plus that has to equal 19. So that's 4. And then I know that 15 plus that has to equal 17. So that's 2. And finally, 4 plus 15 plus 2 plus this blank has to equal 30. And so this is going to be 9. So now I can answer the question, what's the probability that a student studies at least one of these? So the probability of physics union chemistry, that would be at least 1. Well, in this case, that would be, and when I'm doing the probabilities now, I'm not going to rely on these circle numbers. I'm going to rely on these underline numbers. 4 plus 15 plus 2 is the physics or chemistry. They study at least one. These actually study both. So that's 21 out of 30 that are in the sample space. And of course, you can simplify that to 7/10 or just 0.7 if that's what you want to do. The next question is, find the probability that the student studies exactly one of these. So that would be these people or these people, but not these people. So the probability of exactly one And I don't have a special symbol. I could probably work it out with unions and intersections, but I'm going to let it go. That's going to be 4 plus 2, which is 6 out of 30, which, of course, if you simplify, is 1/5. And that's the end of the lesson.